Hello, in this recording, I wish to go over quiz number 20. This question was covered in one of in my previous recording. And here I'm just it's a repeat, I'm talking about it again, but in slightly different order. So here I want to first analyze excuse me. First, let's do some analysis, right? There are a lot of common mistakes, but one of the things I just assume you guys know logarithm properties, which is such as quotient rule, and some of you did not use the quotient rule properly and made that common mistake. So when you apply quotient rule, you basically have a quotient when there's a subtraction of logarithm of the same base. So that's what you get. You don't get not these, okay? Not this one. You've done that, you're making this one of those common mistakes we talk about. Okay, some of you wrote it this way. And you can see that there's a big difference. There's a big difference between the two. The difference is that in this piece, you do the quotient and then logarithm. And in the latter one, you do the logarithm separately, and then you do the division of the numerator and denominator. So, okay, so aside from these common mistakes, there are other mistakes. So when your quiz is returned to you, please feel free to ask if you don't understand why that was a mistake. Okay, so from this analysis, that we understand that we are taking limit of a natural logarithm and x approaching 1 from larger than 1. So the top is approaching 0, the bottom is approaching 0. But we have a function. We have a function here. The question is, can we go through this function? In other words, can we do this and take the limit inside? Okay, can we bring the limit inside? Well, the answer is yes, but it's conditional. There is a condition for us to do that. What is that condition? The condition is that there are two conditions. Okay, I'm going to bring up that theorem, which we talk about in class, right? We talk about in class is that the inside limit, if this limit exists, and the function outside, in our case, f is the ln, and the g is this quotient, right? This is a g, the rule of g. So this piece has to have a limit. Only in this case, we can take the limit across the continuous function. Okay, and I saw that be used, but not some of those is not used properly. So everything you do, you have to follow the theorems, the laws of this mathematics. You cannot create your own. You cannot create your own. Or if you create your own, you must prove it. You must prove it. So it's based on this analysis, right? So naturally, we will show our work. The solution would go by this order, ideally. Okay, you can go slightly different order. So first thing we do is that we prove the limit inside exists. When we present the solution, right? So here's our analysis, and here when we present the solution, we want to present the solution in a logical order, and that logical order is to first we demonstrate that this limit exists. Okay, because only after that limit exists and you're dealing with a continuous function can we apply that theorem. And so we have demonstrated that this limit exists, and therefore we can bring the limit through the function. Okay, so as a result, right, so in this step, then you can just say, well, as a result, right, as a result, then you will have you just bring that limit in place. You bring that limit in place. So this will be the best order. My other version is, you know, I did this first and then I stopped and then, so this is the optional, but I prefer this order. But it doesn't matter which way you show it. You have to demonstrate that this limit exists. Some of you take the limits through it, but if you also show it that you have, you know, demonstrate there's a limit correctly by applying L'Hopital rule, that'll be fine too. Okay, to summarize, when we apply L'Hopital rule, okay, we cannot just apply L'Hopital rule if there's a function. We have to demonstrate that the limit inside exists before we can go through that function. So this will be the best way to present it. The second one, number 2, there were quite a lot of confusion. Some of you equate this piece with the ln of it. Okay, those are, you know, those are pretty obvious mistakes. So we basically introduced, we call this piece y. Okay, with without this limit makes a difference. With without this limit makes a big difference. So we let y equals that at ln y. Okay, you don't operate when there's a limit there. Okay, we know this is always true, and that is true. And then instead of taking limit of y, we're taking limit of ln y. And then we apply L'Hopital rule to the latter expression. When x is approaching 0, the top is approaching, you know, if approaching 0, the bottom is approaching 0. So we can apply L'Hopital rule by differentiating the top by itself and differentiating the denominator by itself. Some of you using, well, it's good that you didn't use a quotient rule, but you use a multiplication rule. Multiplication rule, it doesn't apply here either. You see it as 1 over x multiply ln 1 minus 2x. That's, you know, that's another way of quotient rule. No, please. Okay, so please study L'Hopital rule when it applies. But anyway, so we got the limit of ln y as x approaching 0, and then we applied this property. Okay, this is a logarithm property. Okay, this is a logarithm property. So when we take limit on both sides, okay, this is always true for y is positive. So we can apply limit on both sides. And now this limit is going across another continuous function, e to the power of x, e to the power whatever. And that's how we take the limit to the top of which is exponents. Okay, and then bring that limit, which we found, which is -2 here. So there's a way to express it properly. Okay, if you don't express it properly, and there's someone else, you know, express it properly, then I have to make a distinction between these work. Okay, so please understand the underlying reason behind it and the logical reason behind it. So once again, if you have any questions, please, you know, reach out to me, and thank you for watching.